So far we've only talked about a single first-order equation, y prime equals f of x and y. Now in section 7 we'll talk about systems of first-order equations. These are still ordinary differential equations, that is, there's only one variable, we'll call it x usually, but there's more than one unknown function, or two or could be more, but should normally have the same number of unknown functions as you have equations. So here's two equations for two unknown functions, y1 and y2. They're both just functions of one variable, so this isn't a partial differential equation. Partial differential equations, the solutions you're looking for are functions of more than one variable. There's only one variable here. But two equations, two unknowns. And we'll see that the methods we learned in the earlier sections generalize very easily to systems of first-order equations. And furthermore, if you have a second-order equation, you can write that as a system of two first-order equations. Usually just define y2 to be the derivative of y, so your variables are y and y prime, which we'll call y1 and y2. So the first equation just defines y2 to be the derivative of y1, and then the derivative of y2, that means the second derivative of y1 is equal to a function of f, y1 and y2. In initial conditions, you're typically given y and y prime, so given y1 and y2. So a second-order equation can easily be reduced to a system of two first-order equations. Third-order equation can be reduced to a system of three first-order equations similarly. In particular, we're going to solve this second-order equation here, which we're going to reduce to a first-order system. And we're going to actually solve it using a Runge-Kutta method to show how easily things generalize. The Runge-Kutta method can be used to solve a system of equations. So the system of two equations would be y1 prime equals y2, and y2 prime equals minus 4y2 minus 13y1 plus 40 cosine of x. And this would be y1 at 0, that's y2 at 0, and the true solution for y is given. Okay, to solve that system of two first-order equations, first we need a function which defines the two equations. First right-hand, this basically means y1 prime is y2. y2 prime, which is the second derivative, is 40 cosine of x minus 4 y2, which is y prime, minus 13 y1, which is y. So the input to this function is the scalar x, and the vector y has two components, y1 and y2. Output is the vector f, the two components of f, the two right-hand sides. And here's our Runge-Kutta solver, but y and the right-hand side are vectors. So x is a scalar, it's still a scalar. And y, the starting value of y is a vector. y1 is 3, y2 is 4 at x equals 0. And you pass in each time x and the vector y, and f calculates a vector of two components, f1 and f2. So that will be a vector. k1 is a vector. Scalar, h is scalar, x is a scalar, but y and k1 are vectors. So MATLAB handles vectors. You can't even tell what's vectors and what's scalars unless you look at it closely, because it treats everything as a vector. Basically, scalars are vectors of length 1. So it's actually taking the vector y plus the vector k1 times the scalar h over 2, passing that in, and comes back with two components for k2, f1 and f2. And so k1, k2, k3, k4 vectors. Y is a vector, h is a scalar, k1. And so x goes up by h, y goes up by h over 6 times all that, but y is a vector. Then the true solution, that's y1, that is, we're not so interested in y2, that's the derivative. But the true solution for y1 is that, so the error is y1 minus the true. And I'm going to print out the error for 3 different tests, so I'm going to cut h by a factor of 2 each time, and then print out the ratios. And let's see what happens. The error is the three, when I cut h by a factor of 2, the error goes down from that to that, and then that. The ratios are close to 16, as we would expect for a fourth order method. So programming the Runge-Kutta method or Euler method, it's almost exactly the same as programming it for a system as it is for a scalar equation, single equation. You just have to remember that the unknown, but not the variable, the unknown y, and the right-hand side are vectors, and MATLAB makes that so easy you don't hardly even have to handle them separately. Now I'm going to splice in a portion of the Euler's method for systems section video from Differential Equations, Math 2326. Okay, it's very rare that you can actually solve a system of 2 or more differential equations. Nearly always you'll have to use numerical methods, and we're going to use Euler's method again for a system of equations. It's going to be very, very similar to Euler's method for a single equation. And here they have assumed that the right-hand sides don't have t on it, but doesn't matter for Euler's method. Let's assume that that's a function of the variable as well as the 2 unknown functions, so that's function of t, x, and y. Then every step, t goes up by delta t, which I'll usually call h. So t goes up by h, and x goes up by h times f of the current value of t, x, and y. And y goes up by h times the current value of g of t, x, and y. So there's really only difference between solving a system with Euler's method and solving a single equation is that you've got 2 variables to update, and the rate of change of x depends not only on t and x but on y also, and the rate of change of y depends on x. Otherwise it's pretty much the same. So let's look at an example. Okay, here's a differential equation. X prime is y prime is minus x. Initial conditions: when t is equal to 0, x is 0 and 1. So this table is going to look a whole lot like the tables we did in section 1.4 for a single equation. You start out with the initial value of t, initial value of x is 1, and initial value of y is 0. And every step you say, well, what's the right-hand side of x prime equation? F1 is just y, F2 is just minus x, so it wouldn't matter if this was a function of x, y, and t. You just take the current value of t, x, and y and plug it in there, and that's your F1. Take the current value of x, y, and t here and plug it in, and there's your F2. And then your x increases by 0.5, we're taking a step size of 0.5, times F1. Your y increases by 0.5 times F2. And so F1 is y, F2 is minus x. So x, which is already 1, goes up by 0.5 times F1, which is 0. Y starts at 0 and goes up by 0.5 times F2, which is minus 1. So after one step, x is now 1. It hasn't changed. Y is minus 0.5, so you copy that down here. T goes up by 0.5 every step. You can go ahead and put that in to begin with. And then you calculate now the new value of F1 and F2 based on t, x, and y. And then old value of x plus 0.5 times F1, old value of y plus 0.5 times F2, and get those values. And after 3 steps, we're up to x is down to 0.25, y is minus 1.375. So remember that. We're after 3 steps of 0.5, x is gone down to 0.25, y is minus 1.375. Now let's solve the same problem using DE tools. We use the Euler's method for systems app. And there's a menu of different systems. The first one happens to be exactly what we're solving here. X prime equals y, y prime equals minus x. We're going to start at x equals 1, y equals 0. Draw the field. Now this is an autonomous problem, which means that at each point x, y, the x prime and y prime, the rate of change of x and y don't depend on t, only don't depend on when you get to a point, only what the point is. So to any given xy, you can draw the little arrow. This is the phase plane that we talked about in section 2. So this draws the phase plane since there's no t on the right hand sides. And the exact solution is just following the arrows exactly. The Euler's method is going to follow the arrows, except it only looks down every 0.5 seconds, every t equals 0.5. So it looks down there and the arrows say go straight down. So you go straight down for 0.5 seconds. Now you say, now look at the field and correct. And now it says go that way. So we keep going that way regardless of the fact that the arrows are changing under our feet until a t is equal to 1. And then we take a third step and notice that this is exactly what we got when we did the calculations by hand. After 3 steps of 0.5, x is down to 0.25, y is minus 1.375. And you can keep going, but you're not going to get very good accuracy. If you want more accuracy, you need to take a smaller step size. Okay, here's our MATLAB program. It's the same system. X prime is y, y prime is minus x. But see, if this were any function of x, y, and t, you just put that function there and that function there. So solve a different system, you only have to change these 2 equations. And each step, t goes up by h, x goes up by h times f1, y goes up by h times f2, where f1 and f2 are calculated in terms of t, x, and y. And we're taking a step size of 0.5 so we can get the same results as before. Going out to 6, 12 steps of 0.5 each, go out to 6. Initial conditions, when t is 0, x is 1, y is 0. The exact solution is known. And so let's plot the solution. And this actually takes 12 steps. There's the exact solution, and this is the Euler's method solution. There's our first 3 steps. This is the exact same value that we got by hand or with DE tools. But with MATLAB, you keep going. Then that's pretty large error, so let's cut h by a factor of 10, and it should give much better results. Okay, now I've increased n to 120, so we're taking 120 steps of 0.05 each. And of course it gives better results. Again, this is the solid line is the exact solution. There's the Euler's method solution. It's following the arrows again, but it's looking down more often, so it's following the arrows more closely. The exact solution is following the arrows exactly. We're going to solve one more problem. This is problem 36 in the review exercises of chapter 2. X prime is x times y, y prime is y plus 1. That's a decoupled system, so it's possible to solve this analytically, partially decoupled system, so we can solve it like in the last section. The second equation, y prime equals y plus 1. Linear, you can solve that. Once you solve for y, this is a separable equation, single equation, so you can solve for x. And the solutions are given here as a function of t to compare. And I'm taking 100 steps of 0.01 each. The initial conditions 1 and 0, so should get fairly good solution here. And the solid line is the exact solution that we got by solving that partially decoupled system. And the dots are the Euler's method solution. We can, of course, get even more accuracy by taking h smaller. Okay, your two homework problems in this section. The first one is almost exactly the one we did by hand and by DE Tools and MATLAB, and except that we had y and minus x, and you're supposed to verify that this is a solution: x equals cosine of t, y equals sine of t. If somebody gives you the solution, it's easy to check because it's easy to take derivatives and just check that these two equations are equal for all t. Where they got the solution, this is actually not even a partially decoupled system, because the second equation involves x, the first equation involves y. So how did you solve that? Well, we'll learn in the next chapter, but it doesn't matter if they give you the solution. You can plug it in and check. And then it says take step size of 0.5 out to 10. Well, that would be 20 steps. That's too much to do by hand, and you're not writing MATLAB programs, so just take 3 steps. And then there's another problem. This one is actually fully decoupled because first equation involves only x, second involves only y, so that's pretty easy to solve. But they give you the solution anyway. You just have to check it, and again, just take 3 steps with 0.5.